Welcome back, children. In this video, we are going to talk about the torque experienced by a current carrying loop. This is something that you have already come across in your 10th standard when you are studying about electric motors. I'm going to explain that a little more here, and I will also bring in some equations because you are the 12th standard, so the thing has to get a little tougher than it was in the 10th standard, obviously. So we'll also talk about some equations, but I want to start with that. Let's start with what will happen when you keep a loop in a magnetic field. There are fancier diagrams than this, but let me stick with this diagram because this diagram is a simple diagram and it's easier for you to understand the concept when you explain it using this diagram. So I have a magnet which has two poles, north and south. It's more like a horseshoe magnet or something. Imagine that it's going to join at the bottom. Okay. So you have the north pole here, you have a south pole here, and you also have the current carrying loop in the space between the north and the south poles. So the field is in this direction. Magnetic field is from north to south. I've drawn the field lines here. These are the field lines. B is in this direction. So you have this loop is connected to a battery, and you have a slip ring here. We'll talk about what the slip ring does a little later. But this is the arrangement. It allows what this having a ring like this allows the loop to rotate. So that's the reason why you have it here. We'll now let's see what will happen when current flows through this. Suppose you're closing the switch here, so the current starts flowing through this loop. So it will start from here, the positive terminal, and then it will flow through this part. I'll call this as A, B, C, D, or E, and maybe I'll take it as P, X, Y, Z, A or something. Okay. Because we're going to use other letters, so I'm sticking with this X, Y, Z. So the current will flow through this from X to A to Z to Y, and it will come back to the battery. That's how it does. So if you think about it, if I kept the magnet like this, the north pole like that, and south pole like this, so the magnetic field is in this direction. Okay. Now the current in this wire is going up. So I is in this direction, B is in this direction. Put it this way, B is in this direction. So this will experience a force, and where would that force be? In which direction would that be? So it's going to be IL cross B. So it is IL cross B. Then the force will be acting in this direction. That is, the force will be acting on every part of this conductor. Okay, in this direction, into the board. So the force direction is the force is acting into the board. And now we'll talk about this side. If we talk about this side, the current is flowing in this direction. I is in this direction. B, again as I said, is in this direction only. So IL cross B, then the force is in this direction. So it is out to the board. So the force on this part of the conductor is into the board, and the force on this part of the loop is out of the board. So you can see that if this is the shape of the loop, then this part is getting pulled into the board, and this part is being pushed out of the board. So then you can see a rotational motion. So this will start rotating. The coil will start rotating. Okay. But what will happen if if you keep it like this, like the current direction is the same here, then when it comes to this side, what's going to happen now? The current is still going up, right? Okay, I said like this part is going up, this part is going down. So this is up. So as it comes this side, then it will be up again, and this will be down. Okay, so now let's see what is going to happen. The force is, in which direction the force would be? Same. I cross B, then it's like this. Then this one is down, cross B will be up. So it will start doing this. So this will start oscillating. Okay, you won't have rotation if you just leave the loop like that. So what you need to do is, if you want to make it go continuously, then rotating, then what you should do is, as this part, like where the current is going up, as it comes to this side, then you need to reverse the current direction. If you reverse the current direction, then the force will be now acting in a different way. If this, up till here, the current is going up. The moment it comes here, then you reverse the direction, then the force will now act in this direction out. So it will continue to rotate. It will continue to rotate. Again, as this direction is reversed, as it comes here, then this the direction of the current here would be reversed as it comes here. So the coil will continue to rotate. So your slip rings do that for you. So as the conductor as this loop starts rotating, as it comes to this side, let's see what will happen here first. So this is into the board, this side is into the board, it's out of the board. So as it's going to start rotating like that. So as it comes here, then you see this part is a slip ring, it will come and touch this one. As it touches here, and clearly the polarity will change. Up till here, as it turns, it is at the positive polarity. As it comes to the other side, it will have negative polarity, and direction of the current will be reversed as it comes to the other side. So you will have continuous rotation. So if you don't have a slip ring, then the direction of the current doesn't change. So if the direction of the current doesn't change, then you will have oscillation, not rotation. And that is the function that the slip ring does in this arrangement. Okay? Okay, so this you already know from your 10th standard, or most of you would know it. But what about these conductors? This part and this part. Will they not experience a force? They also pass current. We never talked about them. We always talk about this conductor and this conductor. But we never talk about these two conductors actually. Will they not experience a force? They will experience force too. But notice here, as I said, B is in this direction. Okay? And now you have this conductor. So it's right now, if B is in this direction, the current will stop flowing like this. The current is in this direction, if you see the top of it. Okay? So it is aligned with the magnetic field. It won't experience a force, nor would this conductor in this position. But you see, as it starts rotating, you see there is an angle that is made. Okay? If I keep it like this, then this part is aligned to the magnetic field. But as it starts rotating, you see there is an angle that is made between this conductor and the magnetic field, and these parts will also experience a force. Okay? But it will not result in rotation. Why? Because whatever force this experiences too, then they are in the same direction, you see, this way, and they are collinear. If this experiences a force, and this will also experience a force. Okay? Let's see. Let's talk about the direction of those forces. Okay? Right now, let's say this is in this position. Let's rotate it. Let us say it has come here. So B is in this direction, So this is A, current has gone there, and then it is coming like this, right? It's somewhere, it's like this. So current is in this direction. I, for this conductor, is in this direction. B, as I said, is in this direction. I, L cross B will give me in this direction. So force will be acting upwards. Then look at this conductor. Current will be going through this too. Okay. So then I is in this direction, B is there. So IL cross B will be down. So this will be pushed up, this will be pushed down, this conductor. Okay, but there is no rotation that will result. Because the forces are collinear, they are acting in the same direction. Whatever force is acting here will be acting, the same magnitude will be acting here, but in the opposite direction, like these two forces do. But the difference between these two forces and these two forces is that these forces are collinear. On the same line, they act along the same line. So if I take this body, if I take this and then if I push it in, you know, like I'm using my thumb to push it this direction, and using this thumb to push it in this direction. But if the forces are in the same line, then there is no rotation possible, because there is no motion also is possible. The forces cancel each other out. But if I do it this way, if I push it this way from this position, and if I push the body this way, then the forces actually cancel each other. But then there is a rotational motion, this torque, that will result because of this. So then there is a rotation that is possible because the forces in this case are not collinear. And that is exactly what happens to a loop. Forces act on all the four sides. Okay, but in our example, if you take the top and the bottom part of the loop, then the forces equal each other and they are also collinear. So there is no rotation possible in this direction. Okay, but if you take the other two sides, the forces are equal and opposite exactly, but they are not collinear. Since they are not collinear, then there is a rotation possible in this. Okay, so which way is it you rotate? The force experienced by this part, xy part is into the board and zy part is out of the board. So the rotation will take place like this. Okay. I, B, in, so it's like this. So above the rotational axis, this will be the rotational axis. Start rotating, right? Above the rotational axis, and then it will start rotating like this. It will go like that. So it will start rotating like that. Okay. Now let us see what is the force experienced by this and what is the torque. We are going to do the calculation now. Okay, let us talk about this. What is the force experienced by this? So let's suppose this is length L. This conductor has length L, and let's say this is going to be B. Okay, so this is the width of the loop, the rectangular loop, and this is the length of the rectangular loop. So now force experienced by this is F1, let's say F1 is equal to I is the current flowing through this, L is the length, and then cross B. But in this case, all the time, if I'm keeping the entire loop inside the magnetic field, all the time, the angle is going to be 90 degrees. Notice it. Okay. If it is in this, B is in this direction. So whichever direction this turns, this is going to be 90 degrees to the field. This vertical part of the loop is 90 degrees all the time, wherever it is 90 degrees to it. But this may make an angle, but this will not make any other angle than 90 degrees. So I can say sine IL cross B will give me ILB sine theta, but theta is 90 here, so I'm going to write ILB. That's the force experienced by this. And which way is it? It's going to be I, B into the board. Okay. So that's going to be the force is into the board. But what about this? I'll call this as F2 is equal to same I in same length L, and then B is also same. Again, whatever I said about this part is going to be true for this part too. It will make 90 degrees to the magnetic field, whichever way it is. It's immersed in a magnetic field, and it will only make 90 degrees. So ILB, that's what you get. The sine theta part of it will become 1 all the time, because the angle is 90 degrees. And F1 is equal to F2, but the direction will be towards you. So this direction. Okay? So now this is going to cause a rotation. Okay? Now let's talk about the torque produced by this. Okay, this is a rotational axis, and we calculate the torque for this force. So T1 is going to be equal to F1 into, what will you get now? From here, the distance, what the perpendicular distance, right? That's going to be, this is B, the whole total width of the loop is B, and this is going to be B by 2. So half of that. So B by 2. Okay, so that is what I will get all the time. Force will act in this direction, force will act in this direction, and you see this is going to be like this from the rotational axis, then you will get B by 2 as this one. So that's the torque here. And what about this torque again? So T2 is also is equal to F2 into B by 2. So if I plug in the right things, then I say IL B and then B by 2, that's my torque 1. Then my torque 2 is equal to IL B and then B by 2. Then what's the total torque? The total torque will be is equal to T1 plus T2. So T1 is IL B by 2 plus IL B by 2. Okay, if you add them, then I will get IB into L, B by 2 plus B by 2 will become B. So this is torque. Okay, so the torque is going to be this. But what is L and B? If I take L and then multiply that by B, then that gives me the area of the loop. So I'll say T is equal to I A B, where A is equal to L and L times B. So this is a torque experienced by the loop, the current carrying loop in the magnetic field, in an external magnetic field. Okay, so we have calculated the torque experienced by a current carrying loop. It's given by this expression, torque is equal to I A to B for a single loop. Before I proceed, I would like to talk about a circular current carrying conductor that we came across just a few videos ago. We had a loop like this, then we said like if current I is going through this, then the field, the magnetic field set up by this along the axis of this circle is given by this expression. B was equal to mu naught I r squared by 2 into x squared plus r squared over 3 by 2. So this is what we came across when we talked about the electric field, magnetic field set up by a current carrying loop, a circular loop. Okay, So x is the distance from the center of the circle to the point at which you are trying to find the magnetic field. Let us suppose I want to find the field at a far off distance. You know, like the distance is very large distance compared to the radius of the loop. So x is much greater than r. So that is where I want to find it. Okay. So then what am I going to get now? So if x is much greater than r, like this, I have a loop. Let me draw it in a very. Let me draw a very small circle so that you can understand this. So I have this. This is a coil, and suppose I want to find B at some point here. You see, compared to this distance x, this radius r is very small. So in that case, the B at this point is going to be equal to mu naught I r squared. I cannot do anything to the r in the numerator because it is in multiplication. But when I come down to the denominator, 2 to r can be ignored, because if it is 2 meters and it is just 1 centimeter or something, then clearly I can just ignore that. 2 meters plus 1 centimeter would be 2.01 meters, which is as good as 2 meters. So I can ignore r in the denominator. So I'll get 2 into x squared to the power 3 by 2, because r can be ignored. So that gives me mu naught I r squared by 2x cubed. Well, what it tells you is that if you have a circular loop, or any loop for that matter, even though we've taken a circular loop to explain this concept, if you take any loop carrying current, the magnetic field falls off as 1 by x cube. So that should remind you of something else in electricity. When we talked about electric dipoles in electricity, even there the electric field was falling off as 1 by x cube. So can we compare this to the electric field of the electric dipole? Let me write the expression now and we'll continue. The expression for E, the electric field for an electric dipole, this E is now along the axis of the dipole. We have positive charge, negative charge, so you have a dipole here. Then you are finding E along the axis of this dipole. This was given by this expression 2p by 4 pi epsilon naught x cube. Well, if we add the vector notation to that, and this is what we got. And here P is called as the electric dipole moment. So can I get a magnetic dipole moment, something similar to that? Yes, I can. I just need a little bit of manipulation of this, and then I can get a quantity which is similar to the electric dipole. So let's look at it. Okay, I need a pi here anyway, the denominator. So what I'm going to do is I'm going to multiply this by pi and then divide that by pi. So what I'm going to get now? So I am boxing it. So that gives me mu naught I pi r squared, so divided by 2 pi x cubed. Okay. So what is it going to give me? So this pi r squared I know is what? It is actually, the pi r squared is the area of the circular loop, right? So then I can write this as mu naught I a divided by 2 pi x cube. So I can do something else. I can multiply this by 2 and divide that by 2. And then in that case I'll get, okay, I'll just 2 by 2, then I'll get mu naught by 4 pi x cube to 2 I a. Okay, so you almost got the structure now, or rather you've got the structure, right? So if you see this quantity is mu naught by 4 pi is like your 1 by 4 pi epsilon naught, and then x cube you got there. So 2 is there. So IA can be called as the magnetic dipole moment. It is similar to the electric dipole moment. So I'll say that this is going to be mu naught, or rather I'll say that it's mu naught by 4 pi x cube into 2 to m, where m is equal to IA. So this is what I'm going to call as magnetic dipole moment. And it turns out that if I want to find the magnetic field along the plane, at a point along the plane of this loop, then that is also reflecting, it has similarities with the electric dipole moment along the perpendicular axis that we have already come across in electricity. So like it's an equivalent. It's almost equivalent. It's equivalent to the electric dipole P. So in electricity, you define the dipole as 2aq, and here you are defining it as IA. So once you define it like this, the magnetic dipole moment is equal to IA, then I can come back and I can do this. My torque is equal to mb, because m is equal to IA. Okay, here you have direction. So which direction are you going to associate with? Okay, if you take the electric torque, so what was that? It was the electric torque, T in electricity, T was equal to P cross E. So in this case, the magnetic torque TB, and just assign direction, so is equal to M cross B. You see, it's very similar to that. So P and M. But you need a direction for M. Then how do you assign the direction? So it's the same way. Like, so you have this. I cannot assign a direction to current because I got M. If I have M is equal to IA. Current is not a vector quantity, so I cannot assign a direction to current, but I can assign a direction to the area. We have done that before. So the normal to the area is the direction of the area. But then if I have a loop like this, I have two normal. The normals pointing in two directions. A normal can point in this direction, normal can point in this direction. Then which direction am I going to choose for this purpose? So to do that, I'm going to use the right hand rule again. So if this is the conductor, this is the loop, current carrying conductor, then I'm going to use the right hand rule. So if I do it, you notice if I use a thumb to indicate the direction of the current, then clearly the fingers will go into it like this. So I'll say that it's pointing, the normal is pointing outside. It's like that. So I'm going to use the right hand thumb, the right hand rule, to identify the direction of the loop. So if the current, suppose if I take this, the circular loop is like this, the current is flowing in this direction. So then if I do that, then you notice here, then my fingers point into the board. So the direction of M is into the board. Suppose if this is going this way, I draw it here. The current is flowing in this direction, I, so it's I, moving in this direction. So if you see that the current is moving in this direction, in that case, the direction of the magnetic dipole moment would be towards you. So the direction of M will be this. So this is a convention I am going to use. So now I got a vector quantity also now. That's a word. So it's M is equal to I. So the first expression, IAB, can be written like this. It's similar to your electric torque when dipoles were involved. If you keep a dipole in an electric field, an external electric field, then it's going to experience a torque, and that was given by this expression. So likewise, if you have a magnet, okay, or a dipole, a magnetic dipole, a current carrying loop or something, okay, then if you keep that in an external magnetic field, then it is going to experience a torque which is given by this expression. N is equal to I times the area of that loop. Okay, so this is a general expression. So this led Ampere to believe that all magnetism is caused by the current. So even if you take a lodestone or something, then he thought that there must be some kind of a current flowing inside the lodestone to create this magnetic field, which is true. As I said, like we've not found anything to violate this, except that like in particles like electron and proton, and they have their own intrinsic magnetic moment, but that's a different story. But other than that, like we have not found anything that violates this. Okay. So this is almost true in a way. So this is about it. I hope you understand the discussion. So what we have done is that we have defined a magnetic dipole moment. A current carrying loop is the simplest or the elemental dipole. Okay, we are not found any monopoles, but we discussed it already. So in magnetism there are only dipoles for us. So like the current carrying loop is the simplest dipole we have, the basic dipole we have, and we've done that for only one loop. But suppose if you have multiple loops wound very close to each other, suppose you have n turns of the coil wound very close to each other, the turns, then each circle will be contributing to the dipole, to the field in the same way. So in that case, the the dipole moment for a multiple turn coil, M is given by N times IA, where N is the number of turns. Number of closely wound turns. Okay, so they are very closely wound, then all of them will contribute similarly. So this would be the magnetic dipole moment, or magnetic moment in short. You can generally, okay, magnetic moment is short. Hope you understand this. Okay, we'll get you to problem 4.11 in your textbook. I've given a shortened version of the problem here because I don't have too much space to write that problem. Let me just read that. 100 turn closely wound circular coil of radius 10 centimeters carries a current of 3.2 amperes. So they ask you to find what is the B magnetic field at the center for this setup and the magnetic moment of this coil. Okay, and the second part is you have kept this in an external magnetic field of 2 Tesla vertically. Okay, it's like this. So this field is in this, the external field is in this direction, so you're keeping it vertically. And now it's going to turn. I'll turn that, and then it's from here, and it'll turn all the way to 90 degrees. And they ask you to find what are the initial and final torques, and then what would be the angular velocity when it has reached this 90 degree position. Okay, so that's the question. We'll try to do the problem. We'll try to answer it. First, A. Okay, A. They want you to find B at the center. So for a circular coil, then B at the center is given by, we know that the magnitude is given by the expression mu naught I by 2 R. Okay. So when we do this, mu naught is 4 pi into 10 power minus 7 into I is 3.2 amperes and divided by 2 into this is R is 10 centimeters, so 10 into 10 power minus 2. That's what you get here. So this will be gone, so will be 5 here, and then what you get here, 3.2 into pi. Pi is 3.14, and 3.2, if you multiply that with 3.14, then you get roughly 10. So that will be 10 power minus 4. So you get 4 into 10 into 10 power minus 5 divided by 2 into 10. This 10 will cancel. Then this will be 2. So this is so many Tesla. So you get 2 into 10 to the power minus 5 Tesla. So it's a very straightforward application of the formula. And you take the values and substitute those values in the formula, then you will get the answer. So nothing great about this part. And let's come to B. So B, they want you to find M, the magnetic moment. I said like magnetic moment for a multi-turn coil is NIA. Okay, an easy way to remember this is M is equal to Noi, NAI, Noi. M is Noi. The magnetic moment is Noi. So that's it. So NAI. N is 100 turns. Then ampere is 3.2. And what's the area? Area is pi. Again R squared. R is 10 into 10 power minus 2 the whole square. Okay. As usual, 3.2 into pi will give you 10. So I'll get 1000. It's going to be equal to 1000 here into 10 squared into 10 to the power minus 4. Okay. So what would be the unit of this magnetic moment? And the number of turns, it does not have any unit. A is meter square, the area. I is ampere. So the unit would be ampere meter square for the magnetic moment. So if you 10 power 6 into 10 power minus 4, or 10 power 5 into 10 power minus 4, then you get this 10. So 10 ampere meter square is the magnetic moment. Okay, this B is this. Okay, so this is also very easy to do. So nothing great about it. Things get a little more complicated when you get to the C and D parts of the problem. So what is C? They want you to find the initial torque and the final torque. So think about it. So you have this coil. The problem states that initially the magnetic moment is aligned with the direction of the external field. So we said, like, suppose the current is flowing in this direction. So then the magnetic moment M will be in this direction. The magnetic moment M of the coil will be in this direction, and the external field is also in the same direction. Okay, initially you're hanging it vertically. Okay. So what would be the initial torque for that? So the torque is given by this expression. Torque is equal to M cross B. That's it. Which is equal to M B sine theta, and then we get the direction of the torque. Anyway, so but notice here theta in the beginning is 0 because M is aligned with the external B. So theta is 0. Since theta is 0, initial torque will be equal to 0. Then what about the final torque? Okay, if there is no initial torque, how would it even move? It won't move clearly. So there may be a slight disturbance or something. So you can think about it this way. So B is acting in this direction. So there is this current which is flowing in this direction, maybe, yeah, in this direction. So current is in this direction, B is in this direction, B is here, I cross B. Then the force on this side is going to be in this direction. And here I is here in this direction, up, B there, I cross B in this direction. So force on this side is in this direction and force on this side is the opposite direction. And if it is vertical, exactly vertical, then the forces will cancel each other and no torque will be produced. But if there is a slight disturbance somewhere, then you notice here, then force will be acting in this direction here and in this direction here. So clearly, then you start getting some kind of a torque now. Okay, so you start, once there is a torque, then it will move much further, rotate further, and then again the angle will change, the angle will keep changing, so the torque will also keep changing. The current is same, B is same, but so M is same, but because of this angle, then the torque will be changing. So initially it was 0, so if suppose there is a slight disturbance, then that will set everything in motion and this will move, and this will start rotating. So let's suppose it has come here. So it has moved 90 degrees. Then what would be the torque at this point? At this point, you see B, as I said, is in this direction. M is going to be in this direction. So M cross B, 90 degrees, which will be maximum. So maximum would be when M is perpendicular to the external field. So the final torque final is going to be equal to MB and then sine 90. So it's going to be simply MB. What is M? M is 10 ampere meter squared. And what is B? B is 2 into 10 power minus 5. 2 into 10 power minus 5. Okay, so this is going to be Newton meters now. Okay. So we're going to get 20, so 2 into 10 power minus 4. So this would be the torque. So you start from 0, okay, like you don't have any torque, slight disturbance, okay, then it starts moving, then you have maximum torque here. So from 0, you went to 2 into 10 power minus 4 Newton meter. Okay. So the torque is not constant. The torque is a variable torque. It's a varying torque. So let's come to D now. Then what is the angular speed at 90 degrees? Okay, initially, yeah, it's no change, 0 angular speed, maybe then starts moving, then because there is torque and it is also increasing, then it is, like it's here, as it moves, as it crosses 90 degrees, like as it comes to 90 degrees, then you would have some velocity, angular velocity there, angular velocity will also be there. So they want you to find omega at 90 degrees. And how do you do that? Well, we have this expression, say torque is equal to I alpha. I is, it's not correct now, so I'll use some other symbol, something like this, I. Okay, it's a different I. Okay, I'll maybe. Okay, so torque is equal to I alpha. We know that from our rotational motion, from our 11th standard. Okay, so what is alpha? Alpha is angular acceleration. This I is moment of inertia. So let's say we'll go here. This is going to be equal to I, and what is alpha? Alpha is d omega by dt. The rate of change of angular velocity is the angular acceleration. So I it is d omega by dt. That's what we got here. Okay, so we know the torque. We'll try to do some manipulations now. Okay, we'll take alpha first. Let's see what we can do with alpha. Alpha is equal to d omega by dt. Even before that, okay. This is equal to mb sine theta, right? mb sine theta. Okay. So if I want omega, then I have to take, this will result something like this. Okay. If this d omega is equal to mb by I into sine theta to dt, then I can do the integral. But what's the problem with this integral? This quantity is in theta, but this expression deals with time. Theta is changing obviously with time, but unless you express theta as a function of time, then you can't integrate it. And unless you integrate it, then you won't get the omega, at 90 degrees. Clear, the angle will be from initial to final, right? So that's what we have to do. Okay, anyway. I hope you understand this part, because you can't integrate it, because one is m is constant, d is constant, I is constant, and sine theta is a quantity, but theta is varying with time. You can integrate only with time. You need either express theta in terms of in terms of time, or you can integrate it with respect to theta. You can't integrate with respect to time now. So we'll see like what we can do. So d omega by dt is what we got. So what I'm going to do now is I'll multiply this by d theta and then divide it by d theta. I should be fine. So then I'm going to rearrange things. Now I'm going to get d omega by d theta into d theta by dt. But what is d theta by dt? D theta by dt is nothing but omega, the angular velocity. So it's going to be d omega by d theta to omega. So alpha can also be written as omega into d omega by d theta. So now I have something else to do. I'll come back to this. Once I get this, then I come back and I instead of alpha, I'm going to write omega, d omega, and d theta. Okay, that is equal to, is I alpha, that is equal to mb sin theta. So now it becomes much easier. Mb sin theta. So this will give me this, okay, omega d omega is equal to mb I into sin theta d theta. Now this is an integrable form. Now I can integrate it. Okay. So I go from 0 to pi by 2. And here it's going from 0 to some omega. Okay. So if I do that, I'll get omega squared by 2, omega squared by 2, and that would be 0 to omega. That is equal to, this would be minus mbi cos theta. So minus mb by I cos theta. Then I have to put 0 to pi by 2. Okay. So clearly pi by 2, if I apply the limits, then the first one would be 0, then negative of negative, that will be positive, then I'll put a 0 there, then I'll get mbi. Okay. So this will be omega squared by 2. So I can easily find omega now. So omega squared by 2 is equal to mb by I. So now that will give me omega is equal to 2mb by I square root. Okay. So in the book, I is also given. M you calculated, B is there. MB is, this quantity is 2 × 10⁻⁴ meter. Then if you have I think it's like 1 kilogram meter square or something. 0.1 kilogram meter square. I don't know. So maybe like 1 kilogram meter square. So like you plug in that number, then you will be able to get the value of omega. The I value is given in your problem itself, which I have not taken down here. So omega m you know, B you know, I is in the problem itself. So plug in those values, you will get omega. This is how you do it.